Hey everyone, it's Dr. Walker. This is video 53C on center of mass. Let's start with the concept. The center of mass is a point representing the average position of a system's mass. So when we're talking about a system, we're either considering one object that could just have some random shape. It could be just a particle that is considered a point, or it could be several masses and maybe they're attached together or they don't have to be attached. We can look at all three masses as a system. So whatever configuration of mass that we're looking at, the center of mass is where the average position of that mass is going to be. A thing about the center of mass is that the system moves as if all the mass is concentrated at that point. So up to now, when we've considered an object moving, let's say we had this weird shaped object that was moving, we didn't have to consider the velocity of every single point of that object. We could just say, hey, move with this velocity. What we were unconsciously doing is we were just acting as though the velocity is just acting at the center of mass, and we're just saying, hey, the center of mass has a certain velocity, and we can just consider that the whole object moves with that velocity. One last thing about the center of mass can be explained through this picture. If we look at this picture, it has two masses. We're going to assume that this brown one here is more massive than the blue one. And so the center of mass is denoted here with this X and cm for center of mass. So the average position of the mass is closer to the brown mass just because it's heavier. So if there's a force that is applied above the center of mass, this system consisting of the two masses is going to rotate clockwise. If we apply force below it here, it's going to rotate counterclockwise. But if we apply this force here at the center of mass, there is not going to be any rotation. And this is because the system moves as if all the mass is concentrated at that point. So it's as though instead of having the system of these two masses, we can just pretend there's just a particle here. Particle has no size or shape, it's just a point that has a certain mass, but it's all concentrated at that one point that is at the center of mass. And so when you apply force at that point, there's not going to be any rotation because you're pulling directly where that center of mass is. Let's see if we understand a concept. Let's find the center of mass for each of these objects. So for part A, we're going to assume we have two masses here that have the same mass. So where's the center of mass? Where's the average position of all that mass? Well, it's going to be at the center. It's the average position of all the mass. What about part B? We have a bigger mass on the left, a smaller mass on the right. Well, the average position of the mass is going to be somewhere closer to the bigger mass, right? Because all the positions of this object here have more weight than the smaller mass because this is more massive. And when I said weight, I didn't mean mg, I just mean they factor more into calculating the center of mass. Okay, what about part C here? The center of mass, can you imagine where that's going to be? It's going to be right in the center. That's the average position of all the mass of this object. And finally, what about this hollow ring here? Where is its center of mass? Well, if you think about it, the average position is also going to be in the center. So this tells us that the center of mass does not even have to be inside the object. That's totally okay. Now let's look at how to calculate the center of mass. Let's start with just a system of two particles because I feel like the equation for center of mass is a little bit intimidating. So I like to start with just the equation for when you have two masses instead of a lot of masses. So let's say we have a system that has these two masses here. How do we find its center of mass? Well, we know that it's going to be closer to the more massive object. The way that we calculate it is we multiply each mass by its position. we add the sum of all of those masses times positions, and we divide by the sum of all the masses. So the position does have to be defined relative to some kind of reference point. For this example, let's call the reference point, let's call it right here, x is equal to 0 at the origin. Actually, let's not even do that. We could, but let's actually call the origin, that's the thing, is you can choose where is your origin. Let's call the origin to be at the center of mass 1. It's just going to make the calculations easier. Let's say this is x equal to 0. Now we don't know how far apart these masses are, but let's just assume that the distance between them is d. So that means the position, so x1 would be 0, but x2, right, relative to our origin, x2 is d. And finally, just let's assume that the mass of m2 is equal to twice the mass of m1, just so we can see how this equation works here. Let's multiply our masses times distances. So we're going to have mass 1 times x1 times 0 plus m2, which is 2m1, times x2, which was d, divided by m1 plus 2m1. So the center of mass, we're going to get for its position, we're going to get 2md over 3m. That's going to give us 2/3 d. So I just wanted to show a really quick example just so we could see, yes, indeed, the position of the center of mass is closer to the heavier object, right? It's not right in the center, it's not 1/2 d, it's 2/3 d. It's closer to the heavier object. And I do have that as a note for us. The center of mass lies closer to more massive particles. So this is how we calculate the center of mass if we just have two masses. But we can generalize this to a system having not just two particles, but many, many particles. So to find the position of the x-coordinate of the center of mass, we just add up the products of all the masses times their x position. And then we divide this by the sum of all the masses, which we're calling big M. So this is equal to m1 x1 plus m2 x2. And you can have many, many of them, right? More than just two. And then you're dividing by m1 plus m2 plus m3, etc. So it's the same equation that we just saw before, but now it applies to many, many particles. It just looks a little bit more intimidating, in my opinion, with the summation sign and this big M here, but it's the same exact thing. So if you want to look at the y or z positions, it's the same exact equation. We can also extend this to being in 3 dimensions. So if we're in 3 dimensions, let's say we have many particles. Let's draw a coordinate system here, and we have many particles. And I'm just drawing 2D here, but you can imagine that it's 3D as well. So each mass, each particle has a position vector r, right? R1, R2, etc. Over here, R3. So what you would do is you would add up all of these position vectors, and once again divide by the total mass. Another way to think about it is you could do the x, y, and z components separately, and then just say the x coordinate of the center of mass, that's in the I direction. The y coordinate is in the j direction, and the z coordinate is in the k direction. So we'll definitely do some examples of finding the center of mass of a system that has 2 or more particles.